when you start, and I will.
Yeah, I have started the recording.
Okay, thank you. Thanks. Yeah, fine. Oh, red also. Okay, thank you. So yeah, so last time we were seeing the basics, some more basics of category O, and we ended with the fact that well, then we saw this thing about the Jordan-Holder theorem. That was we saw it in general, and then we applied all these things, including also the center part, the central characters, and so on. That was it. Oh yeah, we classified irreducibles, and these are precisely L lambdas. And finally, we proved that category O has finite. Every object has finite length, so we will just say category O is finite length. Meaning it's a finite length category. Okay, so and then in the tutorial or whatever, what did we do? We proved that. Honey, we proved that category O is finite length, and therefore category O sub is closed under sub object. Under taking some modules. And this was just basically proved by the fact that if you have a finite length module, then it is finitely generated. So if you have a finite length module, you have to take a submodule that is also finite length, and therefore finitely generated. That we showed last time. Okay, fine. So this we all did. This thing last time, and we finally talked about whether it's closed under extensions and subs or not. But that was the tutorial part. Okay, fine. So today, so therefore, as the upshot, maybe I should mention this here. There is a notion. So whenever a category is closed under, direct sums and quotients and submodules. Okay, let's say category of modules is closed under these things. It's called an abelian category. So when it's a category of modules, the form spaces are automatically abelian groups and so on. Anyway, so the upshot of all of these things is that category O is abelian and finite length. It is not closed under extensions. That we already know. Okay, fine. So today, the goal for today is to talk about characters. Okay. So let's start. So first of all, the definition, remember, is that, so given a, maybe I'll just call it a definition. Given an object M O, its character, it's sometimes people say formal character, sometimes they just say character. The point is, for while character formula, it's a finite dimensional module, and those modules have characters, and then sometimes, I don't know if that is the reason why, but most of these objects are infinite dimensional. Okay. Maybe I should do one small thing here before that. I'll just add a remark here. And that's right. Maybe that you should do that in a big size. The point is, category O is finite length. That means that every object in category O has a finite Jordan-Holder series. And all the Jordan-Holder factors are of this form, right? So every MNO has a finite Jordan-Holder series. And any two of those different series have the same set of factors with Jordan-Holder factors, or Jordan-Holder simple factors, simple factors L lambda, lambda in H star. As we said last time, only a countable subset of this, this is a complex vector space, C power I. H star is isomorphic to C power I. And only a countable subset of those are in P plus, so are finite dimensional. Most of these simple modules are infinite dimensional. And so in some sense, most objects in category O are also infinite dimensional because they are made of these factors. Most L lambda are infinite dimensional. I mean, most is just a very understatement. It's all but countably many. It's a measure zero set. Are infinite dimensional, as are most objects M in category. So I just wanted to mention that. So most objects are infinite dimensional. I had said it, I think, last time, purely informally. But now with this understanding, we can sort of make it slightly more precise. Okay, so now definition is formal character. And now this is why I'm saying formal character, because most of these objects are infinite dimensional, not finite dimensional. And we are used to saying characters for finite dimensional representations, whether of finite groups or finite dimensional algebras or even of the algebras. But the formal character of n is, I will sometimes say ch of m, some people say ch of m, some people say char of m. I will use one or the other. So you sum over all lambda in h star, the dimension of n lambda times a formal variable, a formal, formal monomial e power lambda. So the e power lambda is not some e power, it's not a real number or something. It is e power lambda is a formal monomial. For example, the Weyl character formula, of course. For example, let's write down some examples of these. So, for example, one, the character of the L lambda in P plus, is the Weyl character formula, which you have seen earlier. So that was the finite dimensional one. Of course, if you have a, okay. The second, maybe I should just mention that for all finite dimensional modules, if I take character of m plus m prime, what happens in m and m prime are arbitrary objects in category? What happens? Well, you are going to say that each of those is H semi-simple with finite dimensional weight spaces. These are all finite because we said that last time in the previous class. They're finite dimensional weight spaces. Right? So these dimension m lambda are all finite. So now when you take the direct sum of two such modules, what happens? The weight spaces simply unite, right? Then you'd have to take the direct sum of both the modules, but both are H semi-simple. So you end up taking direct sums of all weight spaces. Okay? So what should this be therefore? So think of these guys as formal power series, roughly, some monomials. So in that sense, what should this be? And I should point out, feel free to write these answers. If anybody wants to write rather than speak, feel free to do that in the chat. That's also perfectly fine. Anyone? Okay, so anyway, the point is you just have to say that the lambda weight space of the direct sum is the direct sum of the lambda weight spaces. So the dimensions of the direct sum add up. So this is just character m plus character m. So 1 and 2 together tell you the formal character, in some sense, of every every finite dimensional module. Okay, now let's come to some infinite dimensional modules. Although example 2 also holds for infinite dimensional objects. Now what is this one? This we said last time. This is the character of. So what is this? So it is literally, let's say mu less equals lambda. Now I remember the partial order. Mu less equals lambda. Maybe I'll just remind you here, but you don't need to write it in the notes. Is the same as saying that lambda minus mu is a non-negative integer combination of the simple roots or of positive roots. Or it basically is just a sum of positive roots. So mu less than lambda, and then we write down the dimension of the mu weight space of m lambda times e power lambda. What is the dimension of the mu weight space? This is precisely the constant partition function. It is the number of ways you can write mu minus lambda minus mu as a sum of positive roots, not simple roots. There's only one way you can write it as a sum of simple roots. They are independent. The number of ways you can write it as a sum of positive roots is called the constant partition. Okay, but now let me write this in a slightly different way, like the Weyl character formula, or maybe you have already seen this. I don't know if Ravinder is here, and if he is, can you tell me if you already saw this? Or if anybody else remembers. So maybe I will remind you of this. This is basically a generating function kind of argument that you say, well, this is equal to I claim that this is exactly equal to this, and then remember that the positive roots were always indexed as beta 1 through beta n. This way. And the point being, if you want mu, then you have to isolate the coefficient of, from this product, you isolate the power that is e power minus lambda plus mu. Maybe I should mention here, there's a remark here. Note that here, it's a power series. So how do you multiply terms? Addition is easy. It's component by component.
Not lambda.
Oh, sorry, this is e power mu. Thank you. This is correction. And I should just point out here that power series, you have to know how to add monomials and power series. That is easy, term by term, coefficient wise. How do you multiply? You say e power lambda times e power mu is e power lambda plus for all lambda and open it. That is the convention which you already probably saw for the bicapita formula. So that line should be inserted over here. Okay. So now e power. So the point is that. So if I want the coefficient of e power mu in here, then that means that I need, this is already e power lambda. By the convention that I just wrote, this power series product should give me e power mu. It's a sum of geometric series. It's a product of geometric series. Again, so pi plus is beta 1 through beta n. So right. So from these products of geometric series, I have to multiply monomials from each of them to get a total monomial e power mu minus lambda. That means mu minus lambda should be written as an integer combination of negative roots. That's the same as saying lambda minus mu should be written as a sum of positive. That's the same as this. And now this is precisely geometric series. So it's just e power lambda divided by the product. J goes from 1 to n. 1 minus beta. And you will recognize this term as very familiar if you remember the Weil character formula. It is summation over some W acting on this summation over W that one gets for the Weil character formula. Okay, fine. Okay, so that is that. So this is characters of our modules. Let's do some more. Let's remember. So now remember I defined last time over G equals, sorry, this should be 1A. So yeah, these are examples in 1. So there should be 4, not 3. Maybe I'll call these Roman numerals. So to avoid numbering problems. I. So remember that for G equals SL2 and L is an integer which is bigger equals 1. Lambda is an H star. We define M L lambda as we defined last time to be UG, meaning SL2. Then here you write down e power L, UG, H minus lambda. This is a module generated by one vector, the image of 1, but now e square is 0 or e cube is 0, like that. Okay. And one can check because of the, so by the PBW property, one can check. So maybe I should point out the following. Actually. What is the character of this? So the point is, let me now strengthen. So before I do property 4, let me do 5. Let me do 5, which is strengthening property 2, or example 2, which is it's not just direct sums, but we can also take extensions as long as the extension is H semi-simple. So the same question of H semi-simplicity. So first do 5. Say 0 to m prime to m double prime, usual. But suppose this short exact sequence is in O. So now I know that my middle object is also H semi-simple, therefore all the other axioms then again you can do the same thing. That you can check that the character of M is equal to the character of M prime plus the character of M double. Okay. As a result of that, we can now answer question 4, and I will maybe just. So the point is, we have this filtration of M L lambda. A filtration of M L lambda can be thought of as a succession of short exact sequences. Right? Now back to 4. Back to IV. Back to example IV. That is this one. So we remember the recall. There exists a chain. 0 equals M0, contained in M1, contained in M2, contained in ML equals M L lambda. When the subquotients are, I just mentioned them here. I will mention them with a, let's say, black pen. The subquotients are this one, the highest weight vector, remember here, is e power L minus 1. So M lambda plus L minus 1 alpha. This one is M lambda plus L minus 2 alpha. And the last one, so the last one here is M lambda. That was correct. So these were the coefficients. So now that's what that basically means is that what this basically means is that we have the short exact sequences, right? We have 0 to M1 to M2. M1 is contained in M2. What is the quotient of M1 is M lambda plus L minus 1. Let me just say that. So M1 mod M0, which is M1 itself, is M lambda. So first of all, let me say this. That is the same as 0 to M lambda plus L minus 1 alpha to M2 to M. What is M2 mod M1? It is M lambda plus L minus 2 alpha. Okay, and then similarly now 0 to M2 to M3 to now M3 mod M2 is M lambda plus L minus 3 alpha, etc. Which now means let's start calculating the characters. Therefore, the character of M1, well, M1 was just M1, that's easy, is the character of M lambda plus L minus 1 alpha. How about the character of M2? Well, this is the character of, by the short exact sequence property. By property 5, it's the character of this plus the character of this. How about the character of M3? Now you see the pattern. It is the character of M2 plus the character of this guy, which means L minus 1, L minus 2, and L minus 3. So I'll just write it as summation j equal to 1 to 3, character M lambda plus L minus j. And now there is nothing special about the number 3 or 2 or 1. You can just say character of Mk. J goes from 1 to k. Character. And the final one was ML. So the character of ML. ML, which is ML lambda, is character of ML in this notation. And you can just write this summation down, or you can say this is equal to summation j equals 1 to L. Now lambda plus L minus j alpha. Something is very wrong. That's correct. That's correct. That is e power lambda plus L minus j alpha divided by the product over all the positive roots, because this is the character of the one moment, 1 minus e power minus alpha. And now if you want, this is still, it's again a geometric progression, so you can write this down as, if you want, you can write this down as what, e power lambda alpha, e power lambda by 1 minus e power minus alpha, and then it's 1 plus blah, blah, blah. 1 minus e power minus L alpha. Okay, that's a finite geometric progression. So for example, this is an example of okay. For example, therefore, so yeah, okay. So now let's do, yeah, this was one page. Ready to the whole class for one page. So then okay, so now we have two sets of characters. This was part A, no? Yes. Part A with examples. So now let's do part A. So now we have considered the following two sets of characters. Consider the following sets of characters. One is the characters of all the Algebra modules, as we saw. This is again, of course, over G, not just SLG. Everything is over SLG. And similarly, the characters of these are the biggest highest weight modules of a given highest weight. Because you quotient by the relations that make it a highest weight module or a maximal vector, and you don't quotient by any other relation. So this is always the biggest one. And of course, the smallest highest weight module of a given highest weight is simple because, well, if it was anything not simple, it would have a smaller, it would have a submodule, you can quotient by it, and so you could still further quotient it out. So the fact that you cannot quotient is what makes it smallest, so it's simple. So these are the smallest, so the biggest and smallest modules with a given height. So highest weight modules of highest weight lambda. So consider these two sets of characters. So here are some properties. First, the question is how are they related? Maybe before how are they related, let me point out an observation. So I claim that the first set of characters, the characters of the word mass, are linearly independent. Okay. So first of all, okay, linearly independent in what space? So maybe do I want to define the Grothendieck first? So the thing generated by this. Okay, well, let's put it this way. In the ring of functions, let's say, right? In the formal power series with e power lambdas. So the character m lambda are linearly independent in some space. In
functions which are but supported or countable into integers.
sorry, what?
Character they treat as function from x star or non-integers.
Yes.
With countable.
Countable circle. Sure. Okay, so maybe in the ring, in the vector space, I'll just call it a vector space. Actually, there is a more precise notion than Humphrey's note, which is characters supported on cones, finitely. That's what it says. That is the in the way up, because anyway we are working in category O. So let me call this vector space. We have called some strange name. I will define this space. Okay, fine. Let's say the these characters are linearly independent in the vector space where, so this is Humphrey's. I mean, the symbol itself is not Humphrey's, but this is its formal combinations, the set of all such power series, lambda n star, m lambda, n, I'll call it n lambda, e power lambda, such that all the n lambdas are, it's a vector space.
You can say,
Put C, I guess, R, doesn't matter. Well, let me put Q. Fine. You can put any field between Q and they're independent, so let's put C, biggest possible field. In spite of that, there are no relations. But you could put Q instead as well. Right? So if it's n lambda, it's complex numbers in the that's a C line. Let's reserve n for integer. C lambda lambda, so it's complex, some C linear combinations of these, but these are formal sums. These are not, these themselves are no formal sums. And lambda is, so C lambda is non-zero only for lambda within in a finite union of cones. Lambda j minus the same. We know what this cone looks like. So basically, we are trying to model just the characters in category O. That's what we are really saying. So every object in category O has weights in a finite union. Of course, the C lambda is not equal to 0 for lambda in some finite union, of course. Maybe not for, I don't mean for all lambda. C lambda not equal to 0 implies lambda is in a finite. But it did not mean that for every weight in this finite union, C lambda is. We don't need that. Okay, so this is the vector space where we work with, in which we work. And in this vector space, I claim that these guys are linearly independent. Fine. So I'll prove this. There's nothing to prove. It's one line. And I don't even know what to say. Yes. The point is the character of the one module is just is equal to e power lambda divided by this product. And so how can it be that a linear combination is 0 if you have some summation L equals 1 to R, e power, so C L e power lambda L equals 0. So maybe I'll just say that here. So proof. Say this is 0, then basically you can just multiply of this denominator and just get that all the CL as 0. Maybe I didn't say that, but maybe in the convention that I had e power lambda, e power mu, you should add there that the e power lambdas are linear. So please add that to the convention about e power lambda, e power lambda plus mu. Also add that e power lambdas are C linearly independent. If you add that to the notes, Sushma will of course add it. So that's fine. Official scribe notes will have this extra notation. So almost basically by notation or convention, the Verma module characters are linear. But now let me mention the second thing. Before I mention the second thing, so this is claim 1. Let's write down the definition. Now, what I want to say somehow is that these guys are independent. These guys are spanning. And then these two are actually, it can be recovered from each can be recovered from the other. So they are basically the same set of information. So one is independent, one is spanning, therefore both are basis. Now basis of what? Spanning what? It's not going to span all of this. This is a much bigger vector space. What it will span is the following. What would the characters of L lambda span? If you take integer coefficients. If you take integer coefficients, then okay, maybe I should write down the corollary. Before this, I'll write down the corollary and then I will part D will be definition. So if you take integer coefficients, like if you take positive, in fact, positive integer coefficients, what do we get out of this? And this is exactly example 5 that I have said. If you have a short exact sequence of modules, then the characters add up. So if you take any object in category O, then you know that it is H semi-simple. Uh, did I mention the character of an H semi-simple module at part A in the first at the start of the lecture? Even M in O. Take it. If you take any object in category O, if you can build it up by a chain of submodules, and each the maximal chain from Jordan-Holder theorem. Every successive subquotient is simple, and therefore, as we did for that SL2 ML lambda example, the character of that object of category O is the sum of the characters, because it's just a bunch of short exact sequences put together. Right? So therefore, the positive integer combinations of these guys, non-negative integer combinations of these guys, give you the characters of all objects in category O. But now, because we are working over some sort of group or vector space, we would like to take negative integer combinations as well. So we will write down the group, not just the semi-group, but the group of all integer combinations of these characters. And that is where we will work. And so the first point is, so before we do that, yeah.
Like, assume that lambda L's are distinct and pick the maximal one and say that
Okay, I was going to say look at coefficient by coefficient, but yeah. Okay, so maybe I'll say that. Fine. Okay, fine. Let me start by first of all. Okay, so first of all, remember that these are linearly independent. Let's finish the proof then. Let lambda, so arrange lambda, rearrange, reorder the lambda j, lambda L, such that lambda L is maximal among them. Or maybe I should just say that, so that lambda L is maximal among lambda 1, lambda N for all. So rearrange the lambda, reorder the lambda L is necessary such that lambda R is the biggest, meaning there is nothing bigger than lambda. There are only finitely many of the lambdas, so there is nothing bigger than lambda. If you remove lambda R, there is nothing bigger than lambda R minus 1. If you remove lambda R minus 1 as well, there is nothing bigger than lambda R minus 2. So such that for all L less equal to that, lambda L is maximal among these. There is nothing bigger among these. Now this summation is 0. Then look at this sum. So in CL e power L divided by whatever its product is, you know that this is equal to 0 as a power series or as formal sums, right? So that means coefficient by coefficient, then coefficient of every e power something. The coefficient of every e power anything is 0 on the left hand side because it is 0 on the right hand side. This is equal to summation 0 times e power mu in h star. One point, this is equal to this, right? Therefore, these two power series are equal. So coefficient by coefficient are equal. Monomial by monomial are equal. Now, what is the biggest? So among all the monomials that occur, the biggest ones are clearly lambda L's because all the others are negative roots are subtracted from, right? In Verma module, the highest weights are all these guys. Among these guys, the maximal one is lambda R. So coefficient of lambda R, coefficient of e power lambda R on LHS. There is no way you can get lambda R except through this one. And on RHS it is 0. So CR is 0. Now play the same game because lambda R minus 1 is maximal. Now play this one. Repeat. Repeat via downward induction, I guess. Or just induction. Fine. So this is why this is how you can do write down the formal proof. But basically the idea was sort of clear. Okay, so this is why Verma module characters are independent. Now in particular, maybe I'll write down the corollary. or first a definition. This was still B, right? We haven't started C now. Let's start C. Definition. Fine. Let me just write down the corollary first. The Khare and lambdas are Z linearly independent, meaning with coefficients in Z. In what space? Of course, you can still say in PG, but I can now say I can take in the group. Maybe fine. I'll just say in PG. For now, let's just say that. So either even if the coefficients are not complex but come from integers, obviously this calculation doesn't change. So it's still linearly independent. Okay. So now let me define the Grothendieck group. So now I'm going to actually tell you what you get when you take Z linear combinations of these one module characters. Or if you take Z linear combinations of the simple module characters. So let's start with the just the defining the group itself. Some people I think also call it KFO. The Grothendieck group of category O or of any abelian category. So how do you define the group? Well, one way to do it is with generators and relations. Let's do that. Yeah. As the abelian group, generated by the characters. Maybe let's not call it characters. Generated by by isomorphism classes. Not the characters, as far as I remember. I wrote this down somewhere. ISO classes of yeah. Of objects. So given an object, in category O, M, you write down its bracket to be the isomorphism class. So formal symbol for the isomorphism. Now, of course, the point is, if you have, but you want to say it's a group, so should be some addition, right? And think in terms of characters. As we said, suppose you have a direct sum, then the characters add up. So that same thing should be true here. So that gives you the relation. And more strongly, we wrote in a property Roman 5, what another module of the relations. M equals, maybe I'll start here, M equals M prime plus M double prime whenever you have a short of that sequence. Whenever you have 0 to M prime to M double prime to 0 in category O. So of course these things should all be H semi-simple. Even non-split, yeah. Of course, split also. Whenever you have any extension of modules in category O, the middle equivalence class is taken to be equal to that. So modulo identified this, or you can say equivalent to that. So it's the quotient of this group generated by a huge number of objects, but actually equal to that with this relation. And now the claim is that it's actually it's a very nice group. It's very nicely understandable. Okay. So let's see what it is. Okay, great. So now, first of all, let me tell you a set of generators for this group. Right? So lemma or proposition E. This is what I told you, that the one module characters are linearly independent. And now I'm going to claim that the simple module characters are actually spanning. So we'll talk about the spanning part later, but let's just say Grothendieck group is, maybe I'll call it KF. No, that's fine. Is spanned by, is generated by. In fact, let me even tell you directly. Right? So it is actually a free group. It's a free abelian group. These generate. Clearly, these guys are objects in category O. Therefore, this I don't claim to be independent, but the rest of that part is fine. Right. Or maybe I'll call this a theorem, and we will get to the theorem. Let's call changes to be a theorem. And this is also isomorphic to lambda n star by modules. Moreover, maybe I don't know which one should be first, which one should be second, but these are sort of two independent statements. If you look at the okay, so notice the following: that if two objects are so if I have two modules in category O and they're isomorphic, they are both H semi-simple. Therefore, if they're isomorphic, their characters are the same. So the character is well defined, not just from the module to this ring VG or whatever vector space. It is well defined from vector space. It is well defined from the isomorphism class of a module to vector space. Right? So this character is well defined for all M in category O. Okay. Both the comma should be after this. Yeah. Consider that map. So, yeah, from the Grothendieck group to this vector space VG is a one-to-one map of one-to-one and one-to-one and a group module. Or is a one-to-one group, is a injective group module. This is the theorem that really the character is the isomorphism class is in some sense the same as once you achieve this part, then it's fine. Like the M2 example with the Verma modules, that is equal to that. Therefore, that's fine. That's the isomorphism. So it doesn't matter. So you will also have, in particular, so let me tell you, in particular, in the Grothendieck, there are examples of modules, there are examples of objects in category O, which are not, but which in the Grothendieck group are equal. So you have more, it's a less, you lose some information. Basically.
So, sorry, sir, there is a question.
Yes.
Yeah, so what is equivalence relation here in the Grothendieck, this group, whatever? So he's asking like this Bappa, yeah.
So that
in the chat.
You can say equal to or equivalent to whatever. So you are quotienting by M minus M prime minus M double prime. You take the group here and then you quotient by. So that maybe this remark will tell you that here are two objects which are equivalent but not isomorphic. So that will also help answer. But basically,
no, I am not asking that. Then, so I'm asking, you have taken the isomorphism classes of M. Could you just? Yes. I think you have told already. So can you please recall what is this M? Yes, the isomorphism class.
What is isomorphism class?
I mean, you are taking some isomorphism like the if let's say M and
equivalent if M is isomorphic in this.
Okay. Thank you. Yeah. Okay.
And
Yeah.
because morphisms in O are all G module maps, so this is perfect. That's why isomorphism class is which is module isomorphisms, but every module isomorphism is in category O because every module map is in category. That's why I can just take isomorphism class and not say in O for that. Okay, so remark one can have M is not isomorphic to M prime. Let me give you two examples in SL2. For example, over SL2. Wait, this was D eta. Let's call this F. Remark F. So two examples over it. One is you can look at the Varma module. Let's say you look at the Varma module for 0. Okay. So we know that this contains the Varma module of weight -2. If this was M0, then this is generated by F times M0. And the Weil character formula says the quotient is one-dimensional, L0. So this guy is equal to C times M0. This is generated by M0. This is generated by Fm0. So you can take M to be M0. And then the character of the isoclass of M in the Grothendieck group. Okay, fine. So if you take the isoclass of M0 in the Grothendieck group, then this is equal to the isoclass of M -2. By the way, M -2 is also equal to L -2 because this module is simple. Plus, in the group there is no direct sum. It's a group operation. Addition L0. Okay. Now, can you tell me another object which is not isomorphic to this guy and which is not isomorphic to M0 and yet has the same actual equation? What can another object be? So one clear answer, just like when we talk about characters, is instead of just taking short exact sequences, take the simplest one of them where the terms split. This is just if you take M -2, direct sum L0. This module is not iso. This again, sort of obvious thing. There is obvious short exact sequence. You can take one of these objects in the submodule, the other object in the quotient, or you can reverse that. Right? This object has also the same Grothendieck class. It is this class plus this class. So now the point is these two are not isomorphic.
Yeah,
Sadanand,
Sadanand, are you trying to say something in the chat?
I'm not trying to say anything.
No, Sadanand.
Sadanand, direct
Yeah.
sum. And this is not a direct sum. That's what
No, you asked which object.
Oh, you answered the question. Okay, sorry, I didn't see.
Yeah.
Thank you. Yes, there was an answer given. Sorry, I'm part of it again. So you should go to the chat or something and see it. It was something. And let me, or Irfan can tell me. Okay, so exactly. So that the direct sum is the other option, and these two are not isomorphic. For example, because both of these are, why are they not isomorphic? For example, if there was an isomorphism, then the isomorphism will take the 0 weight space to the 0 weight space. And isom would send M0, 0 to this module with the 0 weight space, but there is no 0 weight space here, so it is just the L0. But then if you take the generator here, M lambda, M0, and you call this generator, let's say V0, or we call it M0 bar. M0 bar. then here F does not kill M0, but F does kill M0. But 0 not equals F M0 gets mapped. Sorry, I want to do it the other way. Maybe. Let's take the isomorphism takes L0 to M0. So let's go this way. If there was an isomorphism, you could reverse it. So you have an isomorphism this way. There is only one dimension of zero weight space, so it has to take this vector to the generating vector. But then, so then 0 equals, but then 0 equals F times the vector of L0, and this should map to F times the vector in M0, and this vector is definitely not 0, M minus 2. So F is the lowering operator in the VR. Right? So this is the combination. 0 cannot be mapping to something else. So they are not isomorphic. Because any isomorphism oh, fine. So here is one example of objects which are not isomorphic. I will write down the other and you can verify by yourself that they are not. It's the same idea. Basically, the moment you have short exact sequences and split or non-split, that gives you the example. So example 2 is basically this module M2 comma lambda that we had discussed, or ML lambda also. So M2 comma lambda equals M lambda plus M lambda plus alpha. But these are not isomorphic. So which is equal to, let me just do the same thing. Okay, now this has to be what do I say? This is the entire, mostly they are isomorphic for the most part. There is only exactly one case where they're not isomorphic. And this is exactly the thing that Raghuram had pointed out yesterday or the day before. And we will get to this subtlety later. Okay? So maybe there's one, I'm not asking you to prove it just yet. We'll see it. This is an example of a non-split extension. Where is my phone? Oh my goodness. Time. Okay, great. So now, sorry, so we were writing down the theorem, right? That this isomorphic. Sorry, what was the theorem? I didn't write it. I just. Let me. We are saying that isomorphic to n lambdas, isomorphic to m lambdas, and one, and second is that Khare from. Sorry. What I mean is that also. So that's right. Okay, great. Okay, so let's write. We will just start to prove the theorem. Right, so let's call it G. Theorem. Let's first work on this character now. So character is well defined on the iso class of a module. So I want to say the character is a one-to-one group. Okay, so define. So let's first of all let's I don't know. Let me call it G tilde be the free abelian group generated by the character of the iso class of M. for all objects. And define the character from G tilde to this vector space Bg by so every free abelian group means it's a elements of free abelian groups are what? They're finite integer combinations of these elements. So direct sum n j and j goes to j goes from 1 to k, let's say goes to summation character of j's times n j. Right? This is clearly a group map. Almost by definition itself. Take some other combination, you add them. There's nothing else to say. So then, okay. Now, but let me also mention now that let's look at the curve. So now also if this is the first homomorphism here, but if it's m0 to m prime to m double prime, 0 and 4, then what do we know? Then we know that m minus m prime. Let me just put m double prime with a plus sign in the brackets. Then goes to 0. Yeah, because we know that this is property 5 or the character of m is equal to the character of this, so you will just add them up. So you get character of m minus character of this minus character of this, which by property 5 is 0. That means that these guys, and therefore the entire subgroup they generate are like in the kernel. So therefore character therefore what is the G modulo of these guys is precisely the Grothendieck group. So the character is indeed a group map. Okay, now the remaining part is the one-to-one part, and that is where the finite dimensional modules and Varma modules come. What do they say? Oh, this is your question. I thought it's the BG. Okay, so this is a group now, right? Because it just factors to the kernel and G modulo the kernel is G tilde modulo this subgroup. Okay, great. Now, why is it a one-to-one map, and where do these Varma module characters and simple module characters come? Right, so let's see. This is maybe okay, fine. Let me. What number was that?
This is Banji.
One is there.
Sorry, Banji.
The theorem was 1f, is it?
मैंने इंटरेंट किया थी के बारे में
नहीं वो तो ठीक है. The theorem was 1f.
मैंने लिखा में वो लिखा इससे पहले वाला लिखा.
1e was remark. Okay, ठीक है. So let's call the theorem as 2a. Let's call this. This is 2b. So I'll continue. So basically 2b and beyond are the groups. So I'll just continue. Okay. Okay, fine. Now what? Okay. So we also already know. No. So I want to one-to-one. So first, let's write down the spanning set. Okay. So this is the group and so on. Okay, fine. Now, so every M in O, this is what we ended with last time. It has a finite Jordan number series. With some quotients which are all the simple objects L lambdas, lambda and H star. So what does this mean? So the isoclass of M is in, or well, maybe even I will number these and then let's say with some quotients L lambda 1, L lambda K, say all lambda as all lambda J in H star. Then what do we know? Because of the same kind of map that we saw that the character of M is the sum of these characters. Maybe I'll say that as well. And the isoclass of M is also the sum of the isoclasses. I could even put character with brackets because I'll just say something. Sick of it. Thanks. And right, so we saw this also. Yeah, we saw the second one already, and the first one is essentially by the same thing. It's the same operation on short exact sequences. You say that it's additive across short exact. Okay, great. So then what do we do? So now that means that okay, so okay, here is the point. That means that every object M can be written as some every isoclass M can be written as some combination of the simple model, right? So this is part. Let me just call it part. We understand that characters and isoclass break down similarly. Now let's talk about the one-to-one. Oh wait, so because of that, in particular, we have reduced that here. In particular, the Grothendieck group of O is equal to. So it is generated by all the so every element in this Grothendieck group. Every such basic element in the group is a combination of these guys. So if you take linear combinations of these guys, so if you take so in particular, maybe I'll do the following. M belongs to summation. The whole we'll talk about the directness later. Lambda in H star. Z integer combinations of L lambda. Okay. Therefore, if you create something like this, if you take a Nj Mj, like we took arbitrary elements here, Nj and Z, combinations, J goes from 1 to whatever I want to call it. I don't want to call it K, let's say I call it L goes from 1 to R, and R and NLML. Right? Whatever. And this is also, it's a finite combination of such elements. So it also lives in this because this set is closed under finite combination. But these guys are precisely all the terms inside the Grothendieck group. So the Grothendieck group lives inside this. Maybe fine, let's call this part. Just going on and on. So let's call this part. I.e. Grothendieck group is sitting inside this direct sum of, sorry, this sum, not direct. The whole point is direct. We are chipping away at this theory. Remember that even when you take sums, whether direct or otherwise, you still take finite combinations, not infinite combinations. So that's what we are doing. And that's all very good because the category O has finite length. So we just care about finite Jordan over C. On the other hand, since these L lambdas are obviously terms in category in this Grothendieck group, so the reverse inclusion also holds. And therefore we get an equality. I'm really spelling this out, going very slowly, but yeah, I'm writing it in full detail. But yes, so the point is the Grothendieck group is a sum of these guys, and it remains to show the freeness, the directness of the sum. Then it's a free abelian group generated by the simple model character. So the final claim, I guess, in some sense, is that this sum is direct. And am I going to prove this? Let's see. I might get stuck in the other stuff and not prove it. Okay, so basically, suppose to prove, hopefully, we'll see. Say I have some, like summation. So let's call this. Let's call this j equals 1 to k. And j l lambda j equals 0, where all nj are non-zero integers. I discard the 0 terms, obviously. That's the in z minus 0. Where all nj in z minus 0 and the lambda j are distinct. And so, of course, you want to talk about pairwise distinct basis elements. Then what do we do? You take the terms. Basically, the idea should be that you take the terms where nj is positive, and you take nj l lambda j here, and this should take the terms to be j negative. I'm not saying that there is at least one term on either side. Maybe all of them are positive. So this is equal to this. Maybe I'll call it k here just to differentiate. But anyway, now what? So now, one thing to point out is this can never happen in the G tilde group because that was the free group spanned by all these isoclasses. So therefore, if it happens in this Grothendieck group, it must be happening in the part you quotiented by. It was an abelian group, so you quotiented by a proper subgroup by those relations. Right? But the whole point is that if you quotiented by the relations, well, okay, what I can just do the following. Fine. This is true in the Grothendieck group. We already know that the character is a one group. This is like sitting here. So since the character is a group map, if these two elements are equal in the group, I can take the characters, and I get these two elements are the same characters. So good. I was myself stuck, but this was perfectly there. So it was meant to be there. It was there. Apply the character map. What do we get? We get n lambda. Sorry, nj character L lambda j equals nj less than 0, sorry, bigger than 0, and nk less than 0 mod nk L lambda k. And now we know what to do, right? Now what do you do? Now what should we do? Somebody answer or I'll ask later. Now what should we do? We just saw this, not just, we saw this argument earlier today. Pick maximum. Among these finitely many lambdas, there is at least one which is maximal among them. That can be on either side, but basically now look at the formal characters. The characters, how do the characters of L lambda look like? Now, the character of L lambda j is e power minus lambda j. So e power lambda. The highest weight space is dimension 1. Everything else is small. So it belongs to e power lambda j plus z bigger equals 0, e power mu less equals lambda j. It belongs to this kind of a sum. Right? And so now if you pick and again I want to say that this power series equals this power series. So entry by entry, monomial by monomial, they have to be equal. So pick the maximal lambda j or lambda k among them. It occurs only on one side and not on the other. So you can never have this equality. As long as this sum is non-empty, you can never have this equality. I should point out, maybe I should say the following. Say lambda is equal to 0, where the sum is non-empty. K bigger than 0, this part you add, all nj are here, and lambda j is. There's at least one thing in the sum. I want to say the sum is direct, so I want to say there's at least a non-empty sum that's 0. So it's where k bigger than 0, and then we will produce a contradiction. So cat this thing is 0. So pick an index. I'll say pick j. Let's say pick j in. Did I just say j to 1 to k and put k here? That's horrible. Let's put j equals 1 to r. Let's put j equal to 1 to r. Sorry, I keep mixing up notation. But fine. Pick 1 less equals j less equals r. Such that lambda j is maximum. Right? Then e power lambda j times 1 times mod nj. What does it say? Then e power lambda j has coefficient mod nj on one side. Why don't I put the nj mod here also? So it's not like I'm only saying it's on that side. Let's put nj modulus here. One as mod nj on one side, which is bigger than 0. Maybe I'll say mod nj bigger than 0 on one side and 0 on the other side. This gives you a contradiction, and therefore the sum is direct. Okay. Yes, exactly. Maybe let's add a remark. Maybe we'll do that after the proof. So remind me after the proof. Okay, but the final point now is, so we proved this thing. We proved that the linear guys are in fact linearly independent. What remains to say is that the Grothendieck group is isomorphic, right? The character, not the character, but the Grothendieck group is so in particular, so character is 1 to 1. That part is done. Oh, is it done? Not yet done. But the same argument works to show the character is 1 to 1. The next claim is that the character is 1 to 1. This is a map from the Grothendieck group to the that vector space VG. The claim is character is a 1 to 1. Proof again, yeah. It's a map of abelian groups, so you can talk of kernel. So suppose summation, but every element inside so by this star, let's label that equation star. So by star, say summation. Let's write the same thing. J goes from 1 to r and j L lambda j belongs to kernel of the character. Of this character map. Then what happens? then you, I just wrote down the same proof. Then that means that the character, if you add the character here, is equal to 0. So the character, this is character of this, which means we come back to this. Then repeat the proof here. And write down the same. Then basically I'll say the same proof as in E. As in E shows that this cannot happen. Well, fine. Let me do the following. Before I do that, let me just say that at least one of these are 0. And not all Nj are 0. So without loss of generality, we can assume that all Nj are non-zero. Now the same proof works. Now the proof in E again goes through. So we have a contradiction. It's the exact same thing. Maybe I could just combine both of those results here, and but then let's do it twice. So this is why the character is one-to-one map, and this is all done. Only thing remaining is that the Grothendieck group is the sum is direct as that. So the last bit remaining, last bit, the Grothendieck, call it Grothendieck group. So I've shown that the Grothendieck group is a direct sum of the simple module spans. Now we show that it's a direct sum of the Varma module spans. Okay, the proof. This is the final part of the theorem. And then let's see how long I have. Oh, I can look at it here. I don't know why I'm looking at my phone all the time. All this should be done. Oh, good. I would have finished at least 2 pages. I can do something over here and then I'll stop. Next time I will do Raghuram's example. Perfect. Okay, we will go up to Sunday. Today is Thursday. 2 more lectures. Okay, so the proof. Let's do the proof. So first of all, obviously the RHS. So let's understand how Varma modules look like, right? So remember that Varma module has the Varma module subjects onto the simple module. And then there is some maximal submodule. Let's maybe call it this N max or whatever. We called it N max already. So recall this is what we have in category O. Great. Which means if I write down the, and what do I know about this guy? First of all, it has a finite Jordan order series because every object in category, this is a sub-object. So therefore category is closer to taking sub-objects. It has a finite Jordan order series. And secondly, all the highest bit vectors, so all only factors that occur. So maybe all factors that occur, all L mu that occur. All L mu in it satisfying what mu is less equals lambda. Right now I'm not even going to central that. So you can do better actually. Maybe I should why don't I take 2 minutes and say that you can do better. In fact, suppose some L nu occurs in it, right? So suppose what does it mean to say that L nu occurs in here? Sorry, one more. Mu less equals lambda and less than but not equals lambda. Why is this true? Because just look at the characters. Look at the lambda weight space. So lambda weight space here. So lambda, I will call it the lambda dimension. The lambda dimension is 1 here. It is a unique highest rate vector. Lambda dimension is 1 here also. Therefore, the lambda dimension here is 1 minus 1. The characters add up. So therefore, the character of this plus character of this equals the character of the Varma. Already the one dimension lambda weight space is accounted for. So the lambda dimension is 0. That's why this is. All the weights of all of these guys are less equals lambda that we knew. But it cannot be equal to lambda because the lambda dimension. I won't elaborate, but it's mentioned. Because lambda in and max of lambda equals 1 minus 1 equals 0. So now, in fact, so these two things are already known, but we know something more. I can even say something more about which, guys, we can improve on the. Let me call this part C. We can improve which L mu occur. So what does it mean for an L mu to occur? If an L mu occurs in M lambda, then you can say what? It means that there is some maximal vector inside some Jordan-Holder series, right? So basically it means that there is some, let's say, n 0 less equals n less equals m less equals m lambda. These are submodules such that m mod n, inside the series, the Jordan-Holder series for m lambda, there is some two terms, consecutive terms in that series, such that n mod n is isomorphic to L mu. But what does that mean? It means that there is some, all these vectors are H semi-simple. That means, i.e., there exists let's call it a V mu in M mu, such that n plus V mu is equal to what? Or what can you say about n plus V mu? Its image is the highest weight vector here. So I want to say that the n plus V mu should go to 0 in here, which means this is contained in n. Okay. But that means but then what can you say? It means that if you look at what n plus V mu, but then okay. But then in this highest rate module, let's look at the highest rate module m lambda mod n. Inside that, m mod n sits inside that. So first of all, let me just say m lambda mod n, which is also the same as un minus or ug applied to the m lambda. So m lambda without the bar is the generator here, and m lambda bar is just m lambda mod n. So modulo viscosity space m lambda bar, m lambda plus. Okay. In this module, n plus applied to v mu bar equals 0. So what does that mean? It means that the center acts by on v mu bar. First of all, it acts by chi lambda, chi mu, but v mu bar belongs to this set. V mu bar is belonging to here. So the center acts on this highest weight vector by chi lambda, therefore here also by chi lambda. Implies that again mu belongs to the twisted y orbit by Harishchandra's theorem. We know this when two, so it implies the central characters are equal, which implies by Harishchandra that the twisted characters, twisted orbit. Okay. So this is the information we have. Whenever, maybe I'm reproving this, I forget, but whenever you have any simple module occurring in a Jordan-Holder series for a Verma module, the highest weights are linked by this twisted while orbit. So, because of that, now I'm going to claim that I'm going to finish the. But let me maybe finish it in the tutorial. So let me just say that. Yeah. So therefore, this lambda belongs to m lambda. Maybe I'll just summarize this and stop here, and then we continue in the tutorial. M lambda module is bigger than 0. This one occurs as at least once in the Jordan-Holder series for m lambda, in any Jordan-Holder series for m lambda, because the factors are the same up to ordering and asymptotic. This implies that mu is less equals lambda, not equal to it. Oh, sorry, not equal to it part is not equal to it is not here. Mu less equals lambda and mu belongs to W. Okay, so this is where I'm going to stop right now. Why is it called? Oh, maybe I should again not call these A, B, and C. I should call this Roman numerals. They are inside G. Are we reading part 2G? Okay. Oh, so I'll continue with part H. This is part of the proof, so I'll keep it inside part G. But let's stop.
Yeah. So can I stop recording, sir?
And yes, characters of L lambda are linearly independent.